Most teams, when they think about secret security, think about storage. Where is the secret kept? Who can read it? Is it encrypted? Those are reasonable questions, but they all assume the secret was strong to begin with, and that assumption is almost never examined. A secret that was generated badly is permanently compromised, not because anyone found it, not because any system was breached, but because its value was predictable from the moment it was created. Every protection applied to it after that point is protecting something that was never actually secret. You can store it in the most hardened vault imaginable. You can rotate it on a daily schedule. You can audit every access attempt. None of that changes the fact that a sufficiently motivated attacker, without touching your systems at all, could have worked out what the value was. This is the vulnerability that never goes away, because it was never introduced from the outside. It was built in at the moment of generation. To understand why this happens, you need a concrete model of what makes a secret strong in the first place. It is not length, although length helps. It is not complexity, although complexity contributes. The property that matters is entropy, a measure of how unpredictable the value is, given everything an attacker might know about how it was generated. Entropy is not a property of the secret itself in isolation. It is a property of the process that produced it. The same string of characters might be high entropy if it came from a cryptographically secure random number generator, and effectively zero entropy if it came from a flawed process that an attacker can replicate. The characters look identical. The security difference is total. Here is a concrete example of how this plays out. A developer needs to generate a session token. They reach for whatever random function their language provides, something like math.random in JavaScript, or the basic random module in Python, or rand in C. These functions are not cryptographically secure. They are designed for simulations, games, statistical sampling, contexts where statistical randomness is enough and predictability is not a threat. They are seeded from system state, the current time, the process ID, sometimes a fixed value. An attacker who knows when the token was generated, or who can narrow down the seed space even slightly, can reproduce every value the function has ever produced. This is not a hypothetical. PHP's rand function, seeded from a timestamp, was used to generate password reset tokens in production web applications for years. Researchers demonstrated that the entire token space could be searched in seconds, allowing password reset flows to be predicted and exploited without any other vulnerability. The application had no known security flaws. The tokens were stored securely. The flaw was in the 6-character generation process that produced them. The fix is not complicated. Every major language and platform provides a cryptographically secure random number generator, one designed specifically to produce values that are computationally infeasible to predict, even with full knowledge of all previously generated values. In Python, it is the secrets module. In JavaScript, it is the Web Crypto API. In Java, it is secure random. These are not interchangeable with their general-purpose equivalents. They are different tools for different threat models, and using the wrong one for secrets generation is a category error that no amount of downstream security compensates for. But randomness alone is not the complete picture. Entropy can be destroyed after a secret is generated, by the way it is handled before it reaches its first use. Consider a secret generated with a perfect random source, genuinely unpredictable, full entropy. That secret is then passed to a key derivation function that applies minimal rounds of hashing, or truncated to meet a length requirement in a legacy system, or encoded in a way that reduces its effective character set from 256 possible byte values to 64 printable ASCII characters. Each of those transformations reduces the search space an attacker has to cover. The secret started strong and arrived weak. The same destruction happens through encoding choices that are made for convenience rather than security. Base 64 encoding is not encryption. It is a representation format. A secret encoded in base 64 is the same secret with a different appearance, but developers who see a long base 64 string frequently treat it as if the encoding itself provides some protection and make decisions downstream about storage, about logging, about access controls that would be obviously wrong if the value were in plaintext. The encoding created a false sense of security that weakened the handling of the underlying value. There is a more subtle entropy problem that affects not individual secrets but populations of them. Secrets generated by humans, passwords, passphrases, PINs, are drawn from a distribution that is far smaller than the theoretical character space suggests. People do not choose passwords randomly. They choose memorable strings that follow predictable patterns, words from a dictionary, capitalized at the start, with numbers appended at the end, with obvious substitutions. A password policy that requires 12 characters, a capital letter, a number, and a symbol does not produce 12-character random secrets. It produces passwords that conform to a handful of structural templates, each of which drastically reduces the search space. This is why leaked password databases are so analytically useful for attackers. Not just because they contain passwords that can be replayed directly, because they reveal the distribution of how people within a specific context, a specific company, a specific country, a specific industry, construct passwords. Once an attacker understands that distribution, they are not searching the full theoretical space, they are searching a much smaller practical space defined by real human behavior. The implication for system design is direct. Anywhere a human generates a secret, the generation process is compromised by human psychology. Anywhere automated tooling generates a secret, the generation process is only as strong as the randomness source it uses. And anywhere those two categories intersect, humans seeding automated systems, developers making choices about which random function to call, there is a gap between what the system assumes about the strength of its secrets and what the secrets actually provide. Secrets management frameworks try to close this gap by taking generation decisions out of individual hands. A secrets manager that generates API keys using a vetted cryptographic source with a defined length and character set produces secrets whose strength properties are known, auditable, and consistent. The alternative, individual developers, individual teams, individual microservices, each making their own generation decisions, produces a population of secrets whose strength properties are unknown, inconsistent, and in some cases severely inadequate without anyone realizing it. The reason generation matters as a foundational topic is that it sets a ceiling. Strong storage, strong rotation, strong distribution controls, all of these improve the security of secrets that were generated well. For secrets that were generated poorly, they are applying rigorous protection to something that was never worth protecting. The ceiling was set at the moment the secret was created. Everything after that operates within it.